Hi, I'm Jay, a visiting researcher at UIUC, and I'm doing my PhD from SUTT Singapore. I would like to introduce our research, EarSense, which was conceptualized with the vision of exploiting teeth as an activity sensor. EarSense is based on the premise that vibration generated from human teeth would conduct through the jaw and skull bones, and eventually arrive at the eardrum. This paper asks two questions. One, can today's off-the-shelf earphones be used to pick up the vibration signals? And two, can we analyze these vibrations and infer the accents or gestures of the teeth and even the teeth locations where such gestures were made? Before describing details, an obvious question arises. Why should we care? We envision a wide range of applications, ranging from healthcare to user interfaces. Consider the case of seizures. Today, patients go out with trained dogs that can alert the patient before the onset of a seizure. However, it has been observed that teeth chattering precedes a seizure. EarSense might be able to detect this teeth activity and alert the patient. EarSense may also be used in remote dental monitoring, where vibration data from the teeth can be uploaded for clinical analysis. In factories or hospitals where workers are wearing gloves or have their hands full, EarSense can be used to perform simple actions or send simple commands. EarSense may also be helpful even in everyday use. A person could type in a PIN number on her phone or click and scroll while wearing a gloves in the winter. Finally, EarSense can help accessibility, such as by replacing the Android switch, which today has to be bought as a separate accessory. Importantly, gestures through earphones would be privacy preserving, support contactless and hand-free sort interactions, and also enhance the usability. So, what makes EarSense possible? Our first pillar is based on the exploitation that commercial off-the-shelf earphones speakers can be programmed as a vibration sensor. The idea is based on the very basic principle of electromagnetic duality. If diagrams of speakers are vibrated through external force, electrical signals are generated in both the channels. Building on this phenomena, we intend to repurpose the earphone as a vibration microphone. In other words, the speaker can act like a microphone and hence can sense vibrations that conduct through the face and skull. But the system in practice would require an automated toggling between the two. And we can do that. We do on-the-fly toggling, which is to and fro conversion of speakers to microphones using software-based jack retasking of pins. Basically, pin 14 to 17 of Realtek audio codec chips were programmed to act as a microphone if there is no sound being played. Having captured the signals at two channels, let's study feasibility of using stereo signals for inferring teeth gestures and locations. EarSense records three types of teeth gestures across 7 locations. These include 3 locations of tap, left, middle, and right, 2 horizontal slides, left to right and vice versa, and 2 vertical slides, up to down and vice versa. An example of left tap is shown in the animation. For EarSense, the teeth gesture inference is a 3-step process. First, we detect if there is actually a teeth-related activity. This classification is based on frequency domain analysis and a study of harmonics. Once we are sure of a teeth activity, we estimate if it is a tap or a slide. The classification between tap and slide is based on analysis of spectral features, template correlations, and signal durations. Taps are impulsive, hence they create a wider band of signal. Once a tap is detected, our next goal is to localize it. Since we have two channels, the intuition says we would use time difference of arrival. But the challenge here is that teeth behaves as a dispersive medium. Vibration signals of different frequencies travel at different speed. Hence, left and right channels are not delayed versions of each other. Since signals are not symmetric, standard delay analysis will not suffice here. As you saw before, signals generated during tap are wideband. Because of dispersion, high frequency waves reach it first to the ear. We find zero crossing instances of the received signals at both the channels. Differences between zero crossing time at left and right channel is calculated. The intuition here is that farther the location of tap from the earphones, more dispersion would be observed. Hence, waves would be more stretched along the time axis. Also, we exploit occurrence of an interesting phenomena. Our cheek muscles move more toward the side of the teeth activity, right before the teeth strike each other. These contractions and relaxations generate waves. We measure energy of these weak waves right before detection of a tap and report about the probable location of an activity. As a whole, tap detection uses fusion of three techniques on the stereo signals: zero crossing differences, dominance of cheek waves, and time difference of arrival of lower frequencies. Using a joint voting, EarSense reports whether middle, left, or right tap was done. If a slide is detected, we exploit a key differentiating opportunity. As can be seen in the animation, the location of friction shifts during a slide. This change of point of contact between teeth leads to variation in relative delays between left and right channel across the time as the teeth move from one end to the other. Hence, we designed a delay profile-based classifier to identify among the four slides. We can use delay versus time profile to classify among horizontal and vertical slides. The delay changes both magnitude and sign as the slide progresses. As can be seen, vertical slides have near zero delays. The delays for horizontal slide span across two extremes. EarSense was evaluated across multiple earphones and target users. Our evaluation proves that the processing chain which we have developed is not only accurate but scalable as well. The performance is uniform across different users for all the gestures. To conclude, this paper claims that off-the-shelf earphones can be used to sense facial surface vibrations. These vibration signals can give idea about teeth gestures and even the location of the corresponding activity. I would like to conclude with a demo video which we foresee as one of the use cases of EarSense. While accessing online portals, when we encounter two-factor authentication, we are mandated to enter OTP codes either through SMS or through some application that we have already installed in our smartphone. How about replacing those numbers with teeth gestures? Let's see how. As can be seen, the screen is showing three teeth gestures to be emulated by the user. And once the user replicates those gestures, he or she will be authenticated. Want it enhance the usability and increase the adoption of TFA, which is already lower than 25%. We request to have a look at our paper for further details. We would be very glad to discuss and push this rapidly evolving field around earable computing. Thank you.